Next up, we have Naveed and Sam. They'll be talking about crafting synthetic attack examples for help training the models. Naveed here is a software engineer and thought leader from the Office 365 security team. He's very interested in applying innovative solutions using machine learning and AI. His colleague Sam is from the Microsoft 365 security signals team, originally from New York, currently based in Cambridge, Massachusetts. And he is particularly interested in mathematical modeling and STEM education. So take it away. Thank you very much, guys.
Is this the clicker?
Yes.
Wonderful. Wonderful. All right. Welcome, everybody. If you have attended previous two talks in this room, there's one thing to discern, is that machine learning in cyber defense is not a science fiction. It's a reality. And for Office 365 team, same is the case. For past 2 years, we have been using machine learning to proactively page our engineers during unannounced pen tests. So in next 30 minutes, Sam and I are going to take you through why and how to use supervised machine learning for cyber defense, and how to overcome some of the challenges in there to ensure that your model that you are going to train is very well balanced, and how to validate that it is really well balanced model. So second thing to discern from previous talks is that there are great minds at Microsoft who are protecting our end customers, the individual customer, the end users. We are not that team. Our team is tasked with protecting the data center, right? So I want you to reset your mind if you have attended previous two talks, because the context is very different, the challenges are very different, and their solutions are very different. So when you are protecting the data center and you want to catch attackers or bad actors, one thing you do is you identify the context in which they might be active. You turn on the telemetry, and this is what you expect, that you are going to find attacker. What really happens is, when you turn on that telemetry, you get this big noise. And if you are one of our old colleague, Dan, you are in trouble, because you cannot really find hackers. So what you do instead is you build rules and filters and whitelists so that you could remove all the service normals so that hackers' activity becomes prominent. This does not work for Office 365. Office 365 is a very dynamic service. It changes from day to day. Its behavior changes. There are so many developers writing code and deploying like crazy, and every day your service is different. So what you want to do is, instead of maintaining those rules manually, you would want to auto-learn those rules. So anomaly detection is one way to auto-learn this rule. This is part of the unsupervised machine learning, and we use it. And if you look at it, it greatly reduces the amount of traces on which we need to generate detections. However, still, there is a lot of detections out there that somebody would need to assess and find hackers, right? So there's one thing to your benefit. And it's a human psychology that if you want to do something and you found a way that is successful, you're going to try to do it again. Humans do it. Animals do it. Hackers do it. No order implied here. So if a technique has been successful in the past, hackers are going to try to use it again. They share their libraries. They share their toolkits. And if it worked at one organization, they want to try it again in another organization. Our pen testers also do it, which are at the top of that stack. So there's something to learn from there. There's something to learn from past stacks, and we use supervised machine learning. And our output is, so we generate out of that close to 440 billion events, we generate up to 5 to 10 paging alerts for our engineers to look at. So to accept that for supervised machine learning, you cannot learn what you don't know, right? But with a world-class pen test team, you can really learn a lot, because they are probing your service in so many different ways. And they are using the same techniques which are being used out there in the wild. And whenever a new attack comes up, they use that technique. They try it on your service and see how it manifests in our service. And you can learn from that. So before I explain to you how we use supervised machine learning and solve some of the challenges, I want you to understand how we transform the user or the human problem of assessing a detection into how we apply machine learning into it, right? So when the detections show up, let's say these are 4 detections on a machine, and the person who is triaging these detections, trying to figure out whether they are malicious or not, they try to dig deeper. So they would try to see if there's any correlation between these detections, right? What was the process that caused this detection? Who launched that process? What's the parent process? Are these multiple detections connected together or not? If they are connected, oh, it looks suspicious. Oh, so it was PowerShell that basically launched this other process. And the same PowerShell connected to an outside IP address, right? So this looks suspicious. I should really dig deeper into it. However, what I think some of the previous talks have also mentioned, that building that graph is very compute expensive. It's very, very hard. It's compute expensive. So there are different ways to solve this problem. And one of the ways is you take n days worth of data. So here, in this example, in this diagram, orange are the detections which are malicious, and light blue or white are the detections which are benign noise, benign anomalous noise on the machines, right? So what we do is we flatten all those detections together. We forget about if there's any correlation between them. We forget about which detection happened before and which detection happened after. But what we do maintain and we do care about is the coexistence of these detections. So when you are applying machine learning, you need to try the simplest solution first and see whether it works or not. How many false positives it generates. And if it doesn't work, then you want to go to a complex problem. So here, we flatten them down. Then we have a feature extractor module, which basically looks at these detections based on some input that it uses. And that input defines what kind of features you want to extract. It extracts some numbers. And this basically, in machine learning terms, this is your feature vector. You apply the same thing on another machine where no malicious activity has taken place, and you got another feature vector. Once you use this technique on all the machines in the data center, you got all the feature vectors. And for the non-malicious examples, for non-machines where you know something bad has happened, you label them malicious. The other one are benign. And we train a model. We use random forest here. And then whenever new activity happens on a machine, we feed that to the model, and model predicts whether it's malicious or benign, and it predicts it with a confidence level. All right, so that's how the level 1 triage is now being performed. Instead of a human, it is being performed by a machine. All right, so next challenge, now again in the context of a data center, not in the context of end user where the previous talk mentioned that you got 1.7 million examples every day. Here, when you are running Office 365 service, there are not enough successful examples. If there were so many successful examples, probably your users have left your service and you're out of business, right? So I'm going to talk about that problem, and my colleague Sam is going to tackle the second problem. So let's dig deeper in there. So the scarcity of successful examples. So we took from Office 365, we looked for the purpose of this talk. We looked at our one workload, which is Exchange, which is one of the bigger workload. And we looked at the data set in 10 days from 825 to 9.4. And there were 150, so there are over 500,000 machines. 156 showed benign anomalous behavior. Compared to that, over the past time, when we have started working on this thing, we have collected 438 compromised machine examples. And they come from past confirmed attacks, which include attacks mounted by our pen test team, and some of the risky behavior that on-call engineers have performed. And we know that they are fixing the service, fixing the customer issue, but we also monitor them and tell them, hey, there's a better way, less risky way to do that. And our pen test team have also automated attacks, which run every hour on a random machine, a random scenario, and we pick the latest examples out of those because every example manifests differently in Exchange. All right, so as you can see, our training set is totally skewed. Very few malicious examples, large set of benign examples. So there's a lot on this slide. So on the right side, the bar chart, it shows us those 500 examples that we had, malicious example. How do they show up in different roles? So role is a set of machines which are performing certain role in Exchange service. Right? So the first one is Active Directory, then backend machine, so forth and so on. And you see the Active Directory is high-value asset, so it is attacked a lot more. Backend machine is where user data is, so it is also attacked. So let's move on to the graph, to the chart on the left. So the blue boxes here are in that role in past 10 days, the samples that we picked. So from all the machines, some of the machines have examples which have these detections. So on the left side, detections, name removed from there. On the bottom, on x-axis, you have the role. So in that role, these detections show up in the anomalous behavior. And orange color is where in that role of all the examples that we got for that 10 days, that detection showed up on all the machines. So as you can see, so the purpose of this heat map is to show you that even the same detection, it may happen only on a few machines. In a different role, it may happen on all the machines. So there's a lot of diversity. Like your population is very, very different in all these subpopulations, which are individual roles. Black dots are the examples, the malicious examples, so which indicates that this detection was present in a malicious example that we have. And you can see the black dots do not cover all of the population here. So we have two problems. One is our malicious examples are very, very few. Number two is they do not cover all the diverse population or subpopulation that we have. So what do we do to tackle this problem? We craft synthetic examples. All right, let's get to it. Oh, before I do that, I jumped ahead. So if you train a model on this thing, what happens is your model performs really, really good, right? Or I'm showing here ROC, area under ROC curve, or area under PR curve. But in practice, so this model has learned this composition, right? In practice, attack can happen anywhere in any of these roles. So when you deploy it in production, it does not perform as well. So let's now get to crafting synthetic examples. So this is a beginner level talk. So I have simplified, and we have simplified all of our theory, or actually all of our things that we are using in production. It's not theory. We are using it. We have very, very simplified it. So here, M1 and M2 are two malicious machines where some malicious activity happened. Malicious activity is shown in terms of detection in orange color. Blue color is benign anomalous behavior. What you do is you extract the malicious signal out of it. Then from your population, you take a sample. And then you overlay malicious signal over benign signals. Basically, you take a union of activity on those two machines. This generates, so when you combine M1 with B1, it generates a synthetic examples, M1, B1. Likewise, you do the same example, same M1 with B2, and M1 with B3. So one malicious example, three benign examples created three synthetic malicious examples. You do the same with M2. That's why it's called Cartesian bootstrapping, because it's a Cartesian product. So what you have achieved here is you got now 6 synthetic malicious examples as well as 2 original malicious examples. All right, so the results. So this was before we applied Cartesian bootstrapping. And this is the white dots are the synthetic malicious example, right? So again, this is original, and this is. So as you can see here, now it covers a lot more population, a lot more subpopulations, meaning that some of these detections are now part of new synthetic malicious examples, which were not before not part of this example. For instance, some persistent technique that was used on BE machine, hackers can use it on AD machine also, right? Some of the example how they talk to their command and control server, for which we have an example on, let's say, front-end machines, it can also happen on back-end machine. So now we cover a lot more diverse population for our malicious examples. On top, in the bar chart in blue, this is during those 10 days, how many examples that we got. As you can see, we have more BE machines. And now with the black bar chart was original. Now with the synthetic example, as you see, the unit on y-axis is very, very different from 50 to 60,000, right? So it represents the population that we have. Now we got a lot more examples for BE machine, and we got examples for so many other roles. All right, so to sum that up, we had close to 500 malicious examples, 150K benign examples using Cartesian bootstrapping. Now we got 84K malicious example, which includes synthetic malicious example. Now you train a model, and from here it looks that this model does not perform as well as the previous model. But again, remember, previous model was an overfit on a composition where we did not have enough examples. Here we had enough examples, and when you deploy it in production, it performs a lot better than the previous model. All right, now I would hand over to my colleague, Sam.
Thank you very much. So now that we've trained our model, we have a second half of the job. The work's not done. We need to be able to measure the performance of that model on a targeted small subpopulation. And in fact, what we're interested in is how well it performs on a particular service, perhaps your service. So when you come to us, we need to be able to tell you, yes, we perform well on your service, your unique scenario, your unique set of background noise. And we have to be able to measure that. But of course, it's a bit more complicated, because each service has machines that are all performing these different roles, like we mentioned earlier. So not only is a subpopulation all of the machines within a service, but now it is a machine in a role in a service. And to really drive the point home, these things are very different. So on the top, we can see how many machines are on each service and just how different those numbers are. On the bottom, we're showing you how different the numbers of machines in roles are within a single service. Order of magnitude difference. In terms of actual behavior, so these charts show you that it's all over the place. So between services, you see very different sets of detections. Within a single service, across roles, very different sets of detections. As we might expect, from the name of a role, we can sort of deduce why it's behaving this way. So there's this big green bar, box plot, right, debug. So that's a lot of anomalous behavior because people are on those machines debugging stuff. New things are happening all of the time on the debug machines. OK, so no talk of measuring success can really be complete unless you discuss metrics. Like, what is the physical number that you are using to know that you've done a good job? We're choosing F-score, which is derived from precision and recall, because those two quantities capture exactly what we're interested in. Precision tells us how much time are our engineers spending on false positive alerts. Recall tells us of the cyber attacks that there were to find, how many did you actually catch? Very important. Now, your typical small subpopulation will have a low number of benign machines and no examples of malicious machines. And if you validate it on this data set, there's nothing to find. Difficult. So what we have to do is we have to borrow malicious examples from other services. Because of the way we've abstracted out the features for these malicious machines, they provide a very good signature of a cyber attack of this kind on a Windows machine, so we can just bring them over. But validating on this data set is also a problem. See, if our classifier says everything in this service is malicious, we have very good precision, because there were very few benign machines. And we have perfect recall, because we found all of the malicious examples. And no service wants to be alerted every single time they do anything, right? So what we need to do is a bit more subtle. We have to start by synthesizing benign examples. right? So we do this until the number of benign examples equal the number of malicious examples. And we do this through a technique called oversampling, which means we can sample them in proportion to the number that they appear. And we can vary them in certain ways. But we have to be very careful to allow them to vary in some ways, but not in others. So imagine that you are a machine out in a service doing your thing, and you're generating some set of detections, some pattern, consistent with what we would expect to see from that service in that role. An attacker lands on that box, starts to try to hack it, and they'll generate their own unique set of detections that may only differ in one or two detection types from what was already happening on that box. So if you generate a synthetic benign example and allow that sort of thing to vary, you might create a sample labeled benign that looks a lot like this actual malicious example. And we don't want things like that in our validation data set. And by the same token, once we have these benign samples, we can bring in those malicious examples, and we can simulate that exact scenario. An attacker is generating this malicious set of detections, so we can join the two sets of detections to create a synthetic malicious machine that's custom tailored to the sort of background noise that's occurring against this service, right? So if in our benign machine we're seeing a detection 1, detection 2, on our malicious machine we're seeing detection 1, detection 3, then our synthetic malicious machine will show you what it's like for both of those to happen. There is an issue here, which is that if you use this simple oversampling technique, rare benign machines can skew the data. And this is highly amplified by resampling. So we're looking into a technique called normalized sampling, which will allow us to craft synthetic benign machines without representing these outliers. And in essence, what we do is we estimate the empirical distributions of how many types of detections are occurring on a machine, discard the outliers. Then we look at what detections occur together and what their counts are, discard those outliers. And finally, with what we're left with, we can oversample. We can sample from those frequency tables. So here's an example of detection types per service over a 10-day period. And I've highlighted some of the outliers in red that we might not want to keep. Here's an example of detections per machine over a 10-day period. Same deal, outliers highlighted in red that we don't want to keep. But why don't we want to keep them? So let's look at this egregious example out in the tail. There are some machines producing almost 40,000 detections. If we look at the furthest machine, what we see is that 37,744 of those detections are coming from exactly one source. From just one detection is causing this to go off the charts, which is a very strong signal that this machine has been misconfigured. And you don't want to synthesize dozens of machines that look exactly like this in order to validate that your classifier is doing a good job, because in fact you'll do the opposite. So to sum up, to make sure that you're performing well on a targeted small subpopulation, what you can do is you can balance the classes by generating benign examples, either through oversampling or through normalized sampling that allows you to craft synthetic examples without representing outliers. And then you can modify malicious examples so that they reflect service background noise. And now when you're validating on this data set, you can be confident that you can tell the difference between a benign machine on the service and a malicious attack on this particular service background. Back to Naveed to close out for us.
Thank you, Sam. So takeaways. Using pen tests and supervised machine learning, you can really learn a lot. And second is, if your malicious examples are not enough and they do not cover all your diverse subpopulation, what do? Craft synthetic examples. And you craft benign examples in order to validate that your model is well-balanced, well-trained, and represents all of those diverse subpopulations. Thank you very much, and then I'll open up for questions.
We've got mic runners on both sides, so if you just raise your hand, we will come to you with a microphone.
So when you're doing the Cartesian bootstrapping, how do you verify that the product is actually a semantically meaningful example?
Yeah. So again, we are in the data center, right? So data center is running Windows machine. So some of the hacking techniques that they use is just regular hacking Windows, right? So if you look at the kill chain, there are certain things in there, persistent, and then going from one machine to another machine, and escalating, and all those things. So they work, if they work on one Windows machine, they likely work on that other Windows machine. So when you take examples from one machine and put them on the other machine, that's what we have seen. If they use the same techniques to do all of those things, they show up the similar. And again, we are talking about, so there are a few things that could be different. The process that they're using, if they're injecting into different processes, because different processes are running on different machines. But remember, we do not use process name as a feature, right? We mostly use Anomaly as a feature. We use some other things as a feature. We cannot disclose everything in there. But we abstract some of the things which can be different in different roles.
How frequently do you tune the model?
So currently, every 3 hours, we train the model, tune the model. And we gave a talk before, like yesterday, which basically gives you all of that scenario that it's continuously training, continuously learning, because your service is continuously changing. And it responds to the change in service, and it adapts to the change in service, and it responds to an active attack. So we have used this during pen test engagement, where model discovered a lot of the machines. It did not know about some of the activity because that it didn't train on. And a human labeled it. As soon as they label it, the next training, when it kicked up, it learned it, and then alerted on 6 other machines which were not discovered by human.
So we need human effort to label the example.
Yeah, well, so when an alert is fired, you need human to respond to it, right? So we need to evict it, and they also confirm it. But we are not throwing human with 10, 100, or 100,000 examples. So we are alerting on specific things that look very, very similar to past non-attacks that we have seen. But when you discover one machine, you easily connect back. How did attacker come to this machine, right? So you find the link very easily. And we have automation built in our system which finds all of those missing links.
Thank you.
You're welcome.
There's one in the back.
Thanks for the really interesting talk. I had a question about kind of building off the last question on how you were, when you were doing your retraining for finding new examples that humans had labeled when you're creating your synthetic malicious machines. How often do you have a sense of how often you find your SMOTE umbrella expanding, essentially?
So again, it's not often that a service, a backend service is attacked. It is very, very easy to attack the end user and customers. So there you see so many examples, 1.7 million every day, new examples. Data center is not attacked often. We have pen test engagement like 2-3 times a year. That's when we see it expanding and labeling new example in model learning new things.
So really interesting talk. I'm interested in knowing how do you know when you create the synthetic example that the malicious intent is still there? There is a possibility that, for example, there is a ransomware, it's executing an encrypting file at a certain frequency. But when you crafted the synthetic sample by your Cartesian product or whatnot, that malicious intent is reduced. It is actually encrypting maybe after 10 minutes per file. So do you strike a balance like, okay, I'm crafting the sample, but now my malicious intent is lost somehow?
Okay, so it's a very good question. There are multiple things involved here. So finding, encryption, and when attackers want to do it in a data center setup, they want to spread fast, right? They want to spread to a lot of machines. There is a different kind of detection which is going to cover it, destruction of data center at fast pace, right? So number 2 is, it also depends on the kind of features that you are using in machine learning from detections. And also, so they are gating mechanisms in there in the model. So in every training, whenever we train the model, whenever we bootstrap, like from the start, we also look at how model performs. And we have automated the whole pipeline, but we have automated it with instilling intelligence into it. So it compares the new model with the existing model, how it performs on the new incoming data, And then it says, oh, now this new model is trained, it doesn't do it as good as the previous model, so it's not get promoted.
All right, let's hear it for Naveed and Sam. Thank you
All right,
very much.
Thank you very much.